Assalamualaikum everyone. So we'll start with our next topic, which is an extension of theodolite traversing. So we are going to study a new method which is called as tacheometry, and which is a very essential topic because this method helps you to determine horizontal and vertical distances using a theodolite. So using the same instrument, which is used for calculating or measuring horizontal and vertical angles, it can, in addition, also give you horizontal distances and vertical distances. So that means you don't have to use a separate instrument for finding out horizontal distances. So you don't have to use a measuring tape or an EDM, uh, since you're working with a theodolite that has a tacheometer inside it, so it can help you calculate horizontal distances with the same setting of the instrument. So that really paces up the work, especially in traversing, where you want to obtain both horizontal control and the vertical control. So that means you need to take both the readings at the same time, and you can do that with the same instrument. So in vertical control, the instrument can work as an auto level as well. So basically, it really paces up the work and reduces the amount of different instruments that you need to use. So this instrument can be used for preparation of topographic maps, where both horizontal and vertical distance are required to be measured. So topographical maps, like we studied in the very first lecture, they tell us about natural features on the man-made features on the surface of the earth. Usually they represent uh, relief. That means elevation difference between the points. So it gives you a basic idea about the land, how the natural topography of the land is changing. This can be used for survey work in difficult terrain where direct methods of measurement are inconvenient. So, like we studied uh, in tape measurement, that it is easier to conduct tape measurement when the ground is leveled, but when the ground is slopy, then it's difficult. And when the surface of the ground has undulations, that means the slope is random. That makes it very difficult. And even when there are obstructions, so that method is not very useful, and this tacheometry can take over the work, and it doesn't have the same constraints. Then we have reconnaissance survey for highways and railways. So if you want to do a quick survey, reconnaissance survey is the very preliminary stage of survey in which you get a general idea about the land, and basically you're deciding about whether to go ahead with the project or not, or if the location is feasible for the project. So then this can work because it helps you in taking a lot of measurements very quickly, and establishment of secondary control points. So like in the case of traversing, where we study that we um, execute or we lay out control points in the field. So control points are the ones whose distance from any reference point is known and whose reduced levels are also known, so they can become as benchmarks. So basically points that can give you information about the land are control points. So what difference is there between a regular theodolite and a theodolite that has a tacheometer inserted? So the only difference is that a simple telescope of a theodolite would give you this vision. So when you're looking through the telescope, you would get this circular vision and just two lines, the diaphragms at 90 degrees and one bullseye. But in a tacheometer addition is that you get these two more lines above the middle line and below the middle line. So in a tacheometer, we call this as upper here, this one as the middle here, and this one as the bottom here or the lower here. And when we are to use with the same telescope, with the same instrument, when we are to take levels, we use the middle here. When we are to take angles, we again take the middle here. But when we want to calculate horizontal and vertical distances, that is where these two additional hairs come in. And just by this addition, uh, we call this as analytic lens, and these are different forms basically representing the same thing. So the main thing is that we have two more hairs which are at equal distance from the middle, whatever the format of or the build of the lens is, but this property will hold. So this actually helps us in determining those distances. And then we have the leveling staff and Stadia rod. So for short distances, ordinary leveling staffs are used, and the difference is that the leveling staff is normally 4 meters long. And for long sights, a specially designed graduated rod is used, which is known as a Stadia rod, and it is also 4 meters long, which may be folded or telescopic. The graduations are comparatively bold and clear, and the minimum reading can be taken as 0.001 meters, which is the least count. So not much difference. We usually use the same leveling staff that we use for leveling to be used in tacheometry, and we're going to stick with that. So how does it work? The principle of tacheometry is based on isosceles triangles. So isosceles triangles are the ones in which at least two sides are equal, and we are going to use one other property of triangles, which is the in similar triangles the ratio of two sides is equal. So if you look at this diagram over here, this point O shows the location of the instrument station, and we have set up our tripod over here, and we place our leveling rods at different distances from the station point or instrument station location. And D1 is the horizontal distance between the point O, where our instrument is, and the point A, where the leveling staff is held in the first series. And then D2 is the distance between O and the point B, and D3 is the horizontal distance between the point O and point C. And when you look at these leveling staffs from the analytic lens or the tacheometric lens, so it had the two hairs, upper and lower. So this is where it bisects the rod, A2 at the upper end and A1 at the lower end, and S1 is the distance between A2 and A1. So A2 minus A1 gives you this S1 distance. And similarly, for the second rod, we have B1, where your analytic lens at the lower here intersects the leveling staff. So that's similar to what we did in leveling, that the bullseye or the middle here, it strikes the leveling rod and you see that interception, and that is the reading you take. In this case, you take two readings, the upper hair and the lower hair, and the distance or the difference between them is S2 in this case, and similarly in S3 in the third case. Now, since there are isosceles triangles, and by taking the ratio of the sides, since there are similar triangles as well, so D1 over S1, which is the horizontal distance between the point O and the point A, and S1, like we discussed, the difference between the upper hair reading and the lower hair reading. And for the second triangle, it becomes D2 over S2. For the third one, it becomes D3 over S3. And what they're trying to tell is that whatever the location of the leveling staff, these ratios remain the same. And this ratio is a constant, and it is equal to F over I, where F is the focal length of the objective and I is the stadia intercept. So this F over I is known as the multiplying constant, and this is a property of the lens. So this would be known, it would remain constant in whatever value you take, and this constant will be useful in finding out the distances. So the theory of stadia tacheometry. So if you see this figure, this V1 is the vertical axis of the instrument. This point O is the optical center of the object class, and your eyepiece is somewhere over here. And this is where your image forms, which is equal to I. So if you see this figure, we have O, which is optical center of the object class, like we discussed. A1, A2, C are the readings on the staff cut by the three hairs. So like we discussed, you have the middle hair, which was always there in leveling and theodolite reversing, but now we have two additional graduations on the lens, upper hair and lower hair. So A1 would be the upper hair reading, C would be the middle hair reading, and A2 would be the lower hair reading. And the distance A1C is equal to the distance C A2. And A1, A2 is equal to I, which is the length of the image. So your image forms over here, and I is the length of the image. A1, A2 is equal to S, which is the staff intercept. So something that we did before. These S1, S2, S3. So they were the difference between the upper hair reading and the lower hair reading. Similarly over here, S is the staff intercept, the distance between the point A1 and A2, which are the upper hair reading and the lower hair reading. And then we have F, which is the focus, V, the vertical axis of the instrument. So this is actually where the instrument is located, the center of the instrument, from where the distance needs to be calculated from the station point to where the leveling staff is. And F is the focal length of the object class. So something that you must have studied in, I think, physics course. D is the distance between optical center and vertical axis of the instrument. So optical center and the vertical axis of the instrument. So this distance is equal to D. U is the distance between optical center and the staff. So your optical center is over here and staff is over here, and this distance is equal to U. And V is the distance between optical center and the image. So the optical center and where the image forms, so basically the length of the whole telescope, so that is equal to V. Now from similar triangles, A1, O, A2 and A1, A2 and O, so these two triangles over here, since the two angles are same, so the ratios of the two sides would be equal since they are similar triangles. So the ratios that they are taken is this I over this distance V should be equal to S divided by this distance U. And if you rearrange these two equations, it becomes I over S is equal to V over U. And from here, you can calculate the distance V, which is the distance between the location where the image forms to the optical center of the object class. And rearranging, you get this. And also, from the properties of lens, we know that 1 over V plus 1 over U is equal to 1 over F, where V was the distance, this one, and U is the distance between the object class center and the staff, and these two added up, inverse of them is equal to 1 over F, where F is the focal length of the object class. And you get this, and you replace the value of V that we had calculated previously, and then we solve this equation. Uh, but let's see where they have introduced these values, D and small d, because what we are interested from the beginning is the distance D, because we want to calculate the horizontal distance between the instrument station, between the vertical axis or the center of the instrument, which is actually the station point, the distance from there to the point where you have placed the leveling staff. So this D is actually what we are interested in. And from this equation, what they have done is that they have calculated it in terms of U, and then they have used the relation that capital D, which is the horizontal distance between the instrument and the leveling staff, is equal to U plus small d. So this capital D is equal to U plus small d. So from here, they've calculated the value of small u and replaced it in terms of capital D and small d. And so at the end, you get this capital D, which is the distance that we want to calculate, is equal to F over I, which is the multiplying constant or the Stadia constant that we studied before, multiplied by S, which is the staff intercept, the difference between the upper hair reading and the lower hair reading, plus F plus D. And this F plus D is the additive constant. Now these two constants, F over I and F plus D, are constant for any one instrument, and they are usually given with the instrument. So you just use their values, and usually this value for F over I for the instruments that we are going to use is 100, and this F plus D is equal to 0. But if the values are something else, so the equation would remain the same to calculate the horizontal distance. Now this is just one simple case, but obviously the actual cases are different, and we'll see some modifications of this equation. So then we have methods of tacheometry. So we have the Stadia method and the tangential method. So we usually always use the Stadia method. So I'm just going to focus on that, and we'll skip the tangential method. So in Stadia method, what we have studied is that the diaphragm of the theodolite is provided with two extra hairs, upper and lower hairs, which makes it a tacheometer. And looking through the telescope, the Stadia hair readings are taken, and the difference in these readings gives the staff intercept. So when you look through the instrument and you note down the upper hair reading on the leveling staff and the lower hair reading on the leveling staff, and you take the difference, that gives you the staff intercept. And then to determine the distance between the station and the staff intercept is multiplied by the Stadia constant, and uh, you get the distance, like the equation that we saw before. And this method can have two different forms. The fixed here method, which is the usual one that we use. In this method, the distance between the stadia here is fixed. So that means you cannot change the distance between the middle hair and the upper hair, and middle hair and the lower hair, and the two which are equal. So you cannot change that distance. So that is called as fixed hair method. And in movable hair method, it's the opposite. You can change the distance between them. And the benefit is that in early times, usually they had the leveling staffs which had graduations, very clear graduations at equal distance, and those were called as target vanes on the staff. And basically, you could change the distance between your stadia here or the crosshairs so that the crosshairs directly intersect those vanes. And since the distance between the vanes was known, so that helped in using the equations which were separate for the movable hair method. But we don't use this method, and we don't use the tangential method as well, so I'm just going to stick with the fixed hair method of the stadia, and all the direct discussion from now onwards will be about this method. So this method can have a number of cases like I discussed before. The case that we discussed in which we came up with this equation that the distance between the instrument and the leveling staff is equal to the multiplying constant multiplied by the staff intercept s plus f plus d, which was the additive constant. Now this equation is valid when the line of sight is horizontal. That means uh, the instrument is going to be leveled, and your theodolite, the telescope of the theodolite is exactly horizontal. That means it would show an angle of 90 degrees, and the leveling staff is also held vertically. So if that is the case, then we use this equation. But usually, due to the undulations in the ground, sometimes the land is such that the staff is held at different points, and you need to change the elevation of your telescope. So that means you'll be looking at the staff at an angle of elevation or an angle of depression. So that would change the equation. But first, we are discussing the very simple basic method, which we try to stick with in the lab as well as much as we can. That the line of sight is horizontal and the staff is held vertically. So in that case, the distance between the station point on which we have placed the instrument and the leveling staff is given by d, and d can be calculated using this simple equation. And f over I is usually 100 and f plus d is usually 0. So basically, in very simple terms, the difference between the upper hair and the lower hair multiplied by 100 gives you the distance. So it's as simple as that. So in one setting of the instrument, you get from the middle hair the reduced level of the station point at which the leveling staff is held, and at the same time, you get the distance between the instrument station and the leveling staff. So instead of doing the two processes separately for gaining horizontal and vertical control, you use one instrument, one setting, one set of readings, and you gain both the horizontal control, that means the distance, horizontal distance, and the vertical control, that means the reduced level of that point. So up till now, we've discussed how to find out the distance between the instrument station and the leveling staff. But now let's see how to calculate reduced level of the point where the leveling staff is actually held. So for that, like we discussed before, that if you want to calculate reduced level of a point, that means you need to know reduced level of some other point, which is the benchmark. So the benchmark is there, and the first reading that you take is on the benchmark, and that is your backside. So the height of the instrument would become the reduced level of the benchmark plus the backside. So that becomes the reduced level of this line, which is the line of sight. So that becomes reduced level of the benchmark plus the backside. Now you have reduced level of this line. And like we have done a lot of times before, now that we have reduced level of this line of sight, whatever reading on the staff we get on the point where the leveling staff is held, whatever the reading is, which is the foresight, you subtract it from the height of the instrument and you get reduced level of the staff station. Now the thing to remember is that whenever we take horizontal angles, vertical angles, or we are to take levels, we always use the middle here. So this is now confusing because before we usually had just one line of sight, but now we have three. One line of sight which gives us upper here reading, the middle here reading is actually the line of sight that we have always used, and then we have another one which gives us the lower here reading. So the two line of sights are inclined and one is horizontal. And when we are taking level, we take the horizontal one. And when we want to calculate horizontal and vertical distances, we use the upper here and the lower here readings. So in this case, we just had to calculate horizontal distance and the reduced level of this point. There was nothing about vertical distance, and we'll get to that in the second case. So in the second case, the difference is that instead of the line of sight being horizontal, the line of sight is now inclined. And the inclination in the first case of this uh, is positive. That means we have an angle of elevation. That means the point where the leveling staff is held is at a higher reduced level. So that means we'll have to tilt our telescope upwards and we'll have an angle of elevation. And that angle of elevation is given by theta, and that theta is actually the angle between the horizontal line of sight. So when your telescope is at 90 degrees and whatever the value is above to it. So that is the angle of elevation. So in this case, the line of sight is inclined, but the staff is held vertically. So, which is usually how we perform this. We'll get to the third case where instead of the leveling staff being held vertical, it is held perpendicular to the line of sight. But we'll get to that. In this case, the leveling staff is held vertical. So this at the point T is where the instrument is held. So we have the tripod and the theodolite, and this is your line of sight when the telescope is completely horizontal. But since with the horizontal telescope you cannot read the leveling staff which is above, so we tilt it upwards to an angle theta so that you can view this leveling staff. And now we have the three line of sights, the middle hair reading, which is over here, the upper hair reading, which would be over here, and the lower hair reading, which would be over here. Now, what we need to calculate is the distance and also the reduced level of this point, and also this vertical distance v, which is the distance between uh, the horizontal line of sight and when it is elevated, the new middle hair reading. So that distance is given by v. Now for this, we have these two equations. The horizontal distance d is given by f over I, which is the multiplying constant like before, multiplied by s. S is the staff intercept, and the staff intercept in this case is A, which is upper here, and C, which is the lower here. Multiplied by cos square theta, and theta is the vertical angle that the instrument is giving you, which is the angle above the horizontal line of sight to whatever your new inclination is. So that is theta plus f plus d, which is the relative constant like before, into cos of theta. And the vertical distance, now remember, whenever we use the term d, capital D, that means the horizontal distance between wherever the station point is, where the instrument is held, and the location where the leveling staff is held. And this v is always the vertical distance between the horizontal line of sight and the new line of sight given by the middle here. So this v always gives you the distance between the horizontal line of sight and the new location of line of sight given by the middle here. Not the upper, not the lower, but given by the middle here. So this becomes V. And this we can calculate it by a similar equation, f4I multiplied by s, which is again the staff intercept, multiplied by sine 2 theta. Theta remains the same again, divided by 2, plus f plus d, additive constant, multiplied by sine of theta. So now that we have the horizontal distance and the vertical distance between the horizontal line of sight and the inclined line of sight, uh, what the thing that needs to be calculated now is the reduced level of this leveling staff station. So this reduced level of the leveling staff station can be given by reduced level of axis of instrument, which is this one, and the reduced level of this axis of the instrument can be calculated, which is the height of the instrument. So you have a benchmark uh, somewhere else, and by taking a reading at the benchmark when the telescope is horizontal, you take the backside and then you add the backside in the benchmark to get this reduced level of height of the instrument, which would be this value. So in order to get the reduced level of this point, we can add this distance v in that value. So now you get reduced level of this point b, and then you subtract this reading that you get on the instrument, which is equal to h. So reduced level of the axis of the instrument plus this value v minus h. Now h is like before the foresight uh, that we have done a lot of times. Just but the difference is that in this case the line of sight is inclined, and whatever the middle here gives you the reading over here at the point B, that reading is your foresight, and that is actually h. So this is how you can calculate reduced level of the leveling staff station. Now in the second case, the difference is that again the line of sight is inclined, the leveling staff is held vertical, but now we have angle of depression instead of angle of elevation. That means the location of the staff station is below the horizontal line of sight. So again, we need to calculate the distance d, which is the distance between the instrument station and the staff station, given by f4I into s, where s is the staff intercept, like before, cos square theta plus f plus d cos theta, and the vertical distance v. Now, the thing to see over here is to remember the definition of the vertical distance, which is the distance between the horizontal line of sight and the middle hair reading. So like before, the distance V was the distance between the horizontal line of sight and the middle hair. In this case, horizontal line of sight and the middle hair, which is now downwards. So this is V. Now, the same equation that we used before, and we get the vertical distance. Now what is left is to find out reduced level of this point P. Now again, we know the reduced level of the instrument, which is the height of the instrument. So again, from the benchmark, taking the backside, you get the reduced level of this line. Now, in this case, the reduced level of the leveling staff station would be smaller than the reduced level of the instrument or the height of the instrument. So in order to calculate that, from the reduced level of height of instrument, you subtract this vertical distance v, and then you subtract the foresight in the inclined case, so which is the middle hair reading. So reduced level of the axis of instrument minus v minus h, you get reduced level of this point p. So this was the second case for when the line of sight is inclined, but the leveling staff is held vertically. Now we'll see the last case in which the line of sight is still inclined, but the staff is held normal to it. Now, this case is not used too frequently, but still, we'll see how this works. So, like we did previously, let's see this picture in which theta gives you the elevation angle between the horizontal line of sight and the new middle here line of sight, and over here the staff is held vertically. If you draw another line which gives you a 90-degree angle between the new line and the line of sight, So the angle between the vertical staff and this newly introduced line would be theta. So if this is theta, the angle between the horizontal line and the inclined line, and over here we have the vertical axis over here, and the inclined line which is at 90 degrees to the previous inclined line. So this angle becomes theta, and we'll use the same thing over here in elevation theta between the, if I call this as the horizontal axis and the vertical axis. So this theta is the angle between the horizontal axis and the inclined line, and over here the staff is held perpendicular to the line of sight. So previously this was the imaginary line, now this is the real line, and the imaginary line now is actually the vertical axis. Now again, the angle between the vertical axis and the leveling staff which is held perpendicular to the line of sight, now this angle again is theta. Now when we calculate the horizontal distance d, the equation becomes this one, f4I into s, where s is again uh, the upper staff minus the lower staff, so the staff intercept. But now in this case, the staff is not held vertically, it is held at 90 degrees to the line of sight, plus f plus d, which is the additive constant, into cos of theta, plus h sine of theta. Now this is different because the staff is held over here, and the reading that we take is at the point B. So this distance d, which it is giving us, is the distance between, or the distance d that we want to calculate is the distance between the point P, which is the location of the instrument, and this point P, where the leveling staff is held. But since that staff is inclined, uh, the distance that we get without using this factor is the distance up till this point B. But now what we need to do is to add this added distance. Now let's see how to calculate this distance. This is theta, and this distance is h, which is the staff intercept uh, foresight, the distance between the 0 point and the middle hair reading. So this is h. Now if you see this smaller triangle, this is the angle theta, this angle is 90. So this can become the perpendicular, this can become the base, and this is the hypotenuse. And this small h is actually your hypotenuse. In order to calculate this distance, we use the sine equation, and this distance becomes h sine of theta. So in this factor, if we add h sine of theta, we get the distance which is actually between the instrument station and this point P. So this complete distance. And similarly, for the vertical distance, now remember the definition of the vertical distance, which is the distance between the horizontal line of sight and the middle here. So this is the equation for the vertical distance. Now what's left is to find out the reduced level of this point P. Now for this reduced level, again we have the height of the instrument. In that we need to add this vertical distance. So now we have reduced level of the point B. Now from this point B, we need to subtract this vertical distance. Earlier, we just used to add or subtract the foresight or the staff reading. But now this staff reading is actually inclined. And what we need is this vertical distance. And this vertical distance is given by h cos of theta. So from the reduced level of the point B, we need to subtract h cos of theta, and we can get reduced level of the point P. Now this is a typo over here. This wouldn't be h sine of theta. This would be h cos of theta. And for the second case, when the angle is in depression, so for this, in order to calculate this distance d, we will get this equation. Now in this equation, the difference is that this point B now is at a farther distance, and we want to calculate the distance up till this point P1. Earlier, this point B was at a nearer distance, and we had to calculate the distance till the point P. So we had to add 8 sine of theta. But now in this case, it's the opposite. We can subtract 8 sine of theta and we get the value of distance. And The equation of the vertical distance is given, and in order to calculate reduced level of the point P, what we will do is we will use reduced level of the instrument station, which is this line. Uh, in this, from this we will subtract the vertical distance V, because the reduced level of this point would be lower, and then we will subtract this vertical distance h cos of theta like before, so that we get reduced level of this point. So now that we understand how the different cases work, now we'll try to apply them in the numericals, and I'll see you in the next